This is the core of a nuclear reactor during refueling. The unloaded assemblies have progressively consumed the enormous energy reserves they originally contained in the form of uranium. Not natural uranium, but as in nearly all nuclear power stations in the world, enriched uranium, the fruit of long preparation. It all begins in the mine, underground, or open cast. A relatively poor ore, 1 to 3 kilograms of uranium per ton, which has to be concentrated and purified. It is sorted, ground, and submitted to a whole sequence of chemical treatments, in which the uranium changes form and color many times. It appears as yellow cake or uranium concentrate. Then ammonium uranate, now as trioxide. Here as tetrafluoride. And finally, as uranium hexafluoride, a gas which is crystallized for shipment in these containers. It is ready to be submitted to a much deeper transformation of quite another nature, enrichment. Behind this cooling tower, a huge plant. It can supply 100 or so nuclear power stations of the 1,000 megawatt range, more than a quarter of world enrichment capacity. These buildings are so wide and so long that they appear squat. Yet they are around 40 meters high. In these containers, uranium hexafluoride, natural uranium, soon to be introduced into this plant for a kind of sorting process on an infinitely small scale, the scale of the atom. Natural uranium contains two isotopes, uranium-235 and uranium-238. Uranium-235, which will undergo fission, is far the less abundant, only 0.7%. Thus, in 1 ton of uranium in the natural state, there are only 7 kilograms of uranium-235. Light water reactors require uranium 4 to 5 times richer, with up to 3.2% of uranium-235, 32 kilograms per ton. That is 25 more than in natural uranium. Such enrichment can only be obtained at the expense of further tons of uranium. To enrich this ton of uranium by adding 25 kilograms of uranium-235, other tons must be depleted, and as much as possible. If we were content to extract 1 kilogram of uranium-235 from every ton, we'd need 25 tons of natural uranium. That's a lot, because uranium is expensive. In practice, about 5 kilograms of uranium-235 can be extracted from every ton. Thus, it's enough to deplete only 5 tons of uranium in an exchange to modify the 235 content, initially 7 kilograms per ton. On the one hand, we obtain 1 ton containing 32 kilograms of uranium-235, uranium at 3.2%. And on the other hand, 5 tons containing not more than 2 kilograms, uranium at 0.2%. The enriched uranium on the one side, and the depleted uranium on the other. The goal of the enrichment plant is to effect such an exchange with natural uranium as point of departure. This exchange takes place progressively due to a series of modules which enrich and deplete at the same time. The uranium fed in is separated into two equal parts. It comes out on one side slightly more enriched with 2 per thousand of uranium-235 more. And on the other side, slightly less enriched with 2 per thousand of uranium-235 less. These slight variations mean that the operation must be repeated hundreds of times in similar modules working in series. The enriched uranium from each of these is conveyed to the inlet of the following module, while the uranium that comes out depleted is fed back to the preceding module. Thus, each module is fed both by the uranium enriched in the preceding module and by the uranium depleted in the next module up the line. Both flows have the same uranium-235 content. These modules, thus linked, make up what is known as a cascade. Progressive continuous exchange gives us an increase in uranium-235 content in one direction, compensated for by a reverse movement of uranium-238. We enrich in one direction and deplete in the other. In the plant, there are 1,400 modules, 1,400 stages, and while each stage enriches and depletes at the same time, we may say that 800 are enriching uranium and 600 depleting it. For natural uranium is supplied at about the middle of the cascade. Starting from this uranium at 0.71%, on the one hand we have the 800 stages needed to obtain the desired degree of enrichment, 3.25%. But this uranium can only be enriched through the uranium-235 extracted from the other side of the cascade. And if we need 600 stages on the depletion side, it is to get the most out of the uranium and finally reject uranium depleted down to 0.2%. Don't forget that the more we deplete, the less natural uranium we need at the entry to the process. If we only need to feed in 6 tons of natural uranium to produce 1 ton of enriched uranium, it is because we reject the uranium depleted to 0.2%, 5 tons of it. This is the principle of the cascade. But what exactly are these stages? They are large elements about 20 meters high, linked by conduits, some going in the enrichment direction and others in the depletion direction. Isotope separation takes place in the upper part, the diffuser. In these tubes, where the uranium circulates in the gaseous state. Thus, the process is known as gaseous diffusion. This is why uranium hexafluoride, UF6, is used. It remains in the gaseous state at low temperatures above 55 degrees centigrade. In each gas molecule, the uranium atom is surrounded by 6 fluorine atoms, all of mass 19. But there are 2 possible masses for the uranium atom, 238 or 235. Total molecular mass is thus 352 or 349, a difference of 3 and about 350. This is very little to differentiate between the 2 isotopes. Now let's see how we go about it. In a gas, the constantly colliding molecules have the same kinetic energy. This means that the heavier molecules, containing uranium-238, move slower than the lighter molecules, containing uranium-235. The faster molecules strike the wall of the containing vessel more frequently. If micropores are put in the wall, the lighter molecules will have more chance to go through than the heavier ones. This leads to slight enrichment of the gas after passage through the wall. These porous walls known as diffusion barriers, take the form of long tubes with billions of holes per square centimeter. The secret of this technique lies in the manufacture of these porous barriers. In each diffuser, there are several thousand such barriers, between two circular plaques, 7 meters apart. The gas inlet is at the same level as the outlet. The gas rises in the upgoing tubes, reaching an upper ring-shaped area where it is channeled to the downgoing tubes. There are fewer downgoing than upgoing tubes, since gas flow progressively diminishes over the journey. Flow is half as much at the outlet. This is the depleted fraction of the gas. The other half is diffused through the barriers, becoming enriched. The enriched gas appears in the low-pressure central area. It is sucked down by a compressor and sent to the next diffuser at slightly under atmospheric pressure. This has the effect of heating it a few dozen degrees. Each stage is composed of 3 distinct parts. The upper part, the diffuser, with the hexafluoride inlet conduit, and the depleted gas evacuation conduit. The enriched gas goes down inside the stage. At the bottom is the compressor to send the gas to the next stage. Between these two units, a heat exchanger compensates for gas heating at each compression. The gas is cooled by contact with the pipe network of a special water cooling circuit. But let's return to gas circulation in the Cascade stages. Each diffuser is associated with the compressor at the base of the preceding diffuser, because it is the one which supplies it with the uranium hexafluoride. The stage is completed with the heat exchanger. Such is the complete stage. The diffuser is fed both by the enriched gas from the preceding diffuser and by the depleted gas from the following diffuser. A conduit feeds it back to the same compressor. This is how the Cascade's various enrichment stages are hooked up. The size of the elements is impressive. This is just the upper part of the stage, the diffuser. This is the base, housing the compressor. And the intermediate part, the heat exchanger, containing the cooling tubes. In the plant, the stages are set out in vast adjacent halls, each with a group of 20 stages. The uranium hexafluoride from the preceding group is moved by an initial compressor, the only one not topped by a diffuser. The gas becomes more and more enriched through the 2 ranks of stages until reaching the last diffuser, which has no compressor. The gas which comes out is fed to the compressor on the next group. Feedback of depleted gas is in the opposite direction. This time, conduit link is between the 2 ranks of stages and not on the outside. Let's take a closer look at gas circulation. There are 2 flows in opposite directions. One towards enrichment, the other towards depletion, progressing from group to group. A group can be isolated for maintenance from the rest of the plant. This makes for great suppleness of operation. It takes 70 of these 20-stage groups to make up the 1,400 stages of the Cascade. Groups are located on both sides of a central aisle in each of the plant buildings. Buildings are designed on the scale of the huge units they house. This diffuser, when set up with its companions in a group of 20, will be streamed through by uranium hexafluoride at around 100 degrees centigrade. Almost throughout, gas is at lower than atmospheric pressure. But not all stages are the same size. The complex theory of enrichment requires that throughout the cascade, from the natural uranium input to both ends, hexafluoride flow, instead of being even in all stages, must be greater near input and diminish progressively towards the extremities according to this ideal curve characteristic of enrichment plants. In theory, each of the 1,400 stages should be different. In practice, to facilitate stage mass production, only 3 stage sizes have been selected. Stages differ in height, weight, and compressor power. Each size is set up in groups of 20. Given these 3 stage sizes, the number of groups of each size was selected for optimum approximation to the theoretical curve. This accounts for the layout of the plant's 70 groups, 40 on the enrichment side and 30 on the depletion side. All these groups are set up in the plant's 4 buildings. The largest houses the large-size depletion groups. The next houses the large-size enrichment groups. Then the same building houses the medium-size enrichment and depletion groups. And the smallest building houses the small groups at both ends of the cascade. So throughout the plant, all these adjacent stages with natural uranium as the starting point lead on the one side to uranium enriched to more than 3% and on the other to uranium depleted to around 0.2%. The total making up the 70 groups and the 1,400 stages of the cascade. While in these 4 buildings, the uranium hexafluoride is being diffused and rediffused ceaselessly through thousands of kilometers of barriers, the heat transmitted to the gas by compression must be removed. This is the role of the cooling towers. The water heated in the heat exchangers loses its calories here before being recycled to the plant in closed circuit. Finally, enrichment requires electricity. The power and number of the 1,400 compressors permanently absorbs the energy provided by 3 of the 4 reactors of the nearby nuclear power station. 3 reactors to run a plant which provides enriched uranium for more than 100 others. A plant which can assure long-term nuclear fuel supply for Belgium, Italy and Spain, France's associates in this enterprise, and for many other customers. Every year, these containers bring more than 25,000 tons of uranium hexafluoride to the plant. At the plant exit, in smaller containers, the same chemical product comes out, but with a far greater wealth of energy. Soon, this low-enriched uranium will be fuel for a reactor after final, more traditional modifications and various industrial processes. Now it is in the form of tiny uranium oxide pellets, soon to be placed into fuel rod assemblies. Every year, thanks to the Cascade enrichment plant, about 5,000 such assemblies can be produced, the equivalent of 150 million tons of oil.